Hi everyone, today we're looking at finding and choosing phenomena. To review, what is a phenomenon? Remember, a phenomenon is something in the natural world that students are trying to figure out. A good phenomenon is one that sparks curiosity and wonder. It's personally relevant to students, it addresses the performance expectations so it's aligned to your standard, and it can be investigated. Students are able to investigate it. I want to start this video with this quote from nextgenscience.org because I think it really does a great job of explaining why phenomena can be so powerful when used in the science classroom. It says, by starting a unit or lesson with a phenomenon, students are able to identify an answer to why do I need to learn this before they even know what this is, right? So they're grappling with the phenomenon, interested in the topic, understand why it's personally relevant to them without even knowing that your unit that's upcoming is going to be about forces or cells or something like that, right? It provides the motivation they need to learn the content before they even know what the content is. Now, there's two types of phenomena that are important to distinguish when you're planning a unit. The first is called an anchoring phenomena, and the second is called an investigatory phenomena or a building phenomena, it's often called. Anchoring phenomena tend to be more complex, whereas investigatory are less complex. The reason an anchoring phenomenon is complex is because it is anchoring the unit. It is what the class is ultimately trying to explain in this unit, right? It encompasses as much of the unit as possible. An investigatory phenomenon is a segment of the anchoring phenomenon that allows students to more easily focus on a part of the overall learning, right? So it's something that students will focus on for a day or two or a week or something like that. Whereas the anchoring phenomenon is really going to be something they're revisiting all throughout the unit. Because of that, the anchoring phenomenon, there's only one per unit. Investigatory, there's multiple. And last but not least, when we talk about that assessment, it's the understanding of the anchoring phenomenon that students are going to transfer that knowledge on the assessment to a novel phenomenon. Um, Remember, we'll talk about this a little bit later, but the assessment shouldn't be asking about the anchoring phenomenon, right? The anchoring phenomenon is something that your class is working with, talking about, explaining throughout the whole unit. But the assessment involves a novel phenomenon where students are able to transfer that understanding. So, a really quick hot tip from my experience as a science teacher is to name your unit based off your anchoring phenomenon. I teach ninth grade biology. Initially, our first unit of the year used to be called cellular processes. However, the phenomenon that we use, the anchoring phenomenon that we use in that unit, is juvenile Huntington's disease. Students watch a video where they hear from kids who suffer from juvenile Huntington's disease, and then throughout the unit, their goal is to figure out what causes it, what cellular processes are involved in the symptoms, etc. So I renamed on my learning platform, right? Google Classroom for me. I renamed the unit Juvenile Huntington's Disease just to make it super clear to students that like the purpose of this unit is to understand this phenomenon, it's to figure this phenomenon out and answer the questions we have about this phenomenon. That's what this unit's about. That's just a hot tip. Another example of anchoring versus investigatory. This is from a middle school science class I taught related to this Earth Science Standard. This Earth Science Standard, for those middle school Earth Science teachers out there, if you know it, it's a really, really meaty standard. There's a lot to it about regional climate. So my anchoring phenomenon when I taught this at an international school in Bogota, Colombia, was this map, right? This map is a Köppen-Geiger climate map that shows the various different climates within Colombia. As you can see, there's a lot of different climates. Students ask questions, like what's happening up here? Why is the climate so distinct over here? What's here, what's causing all these different climates, right? They ask those questions. And our goal throughout the unit that we came back to repeatedly was figuring out this map, how this map, or specifically why so many different climates exist in Colombia, right? Students are familiar with things like altitude and latitude. They might not know why it affects climate the way it does, but they're familiar with the fact that it does affect climate. But there are a lot of other factors that students aren't familiar with. So in order to get them to understand how those factors affect climate, we then brought in these investigatory phenomena, right? These primary four ones. The first one, we compared these two cities, Kansas City in the United States with New York City. Both are very similar latitude, similar in a lot of ways. However, New York City is close to water and Kansas City is far from water, right? So by investigating this, we're able to figure out how proximity to water affects climate. Then we looked at Dublin, Ireland versus Nain, Canada. Two places, once again, similar latitude, similar proximity to water, but Nain, Canada is far colder in order to learn how ocean currents affect climate. Then we try to figure out these two cities, right? Once again, very similar in many respects. However, the only difference is the relation to mountains or landforms and to see how proximity to mountains affects climate. And last but not least, we looked at data related to urban areas in Arizona versus rural areas of Arizona. to determine how urbanization affects climate, right? So we used those for investigatory phenomena to build up to an understanding of our anchoring phenomena. So we return to the anchoring phenomena throughout, and of course at the end of the unit. To go back to that hot tip I mentioned earlier, perhaps I could call this unit Climate in Columbia, or this might be a little wordy, but I could even bring in the cross-cutting concept for this unit and say using system models to understand climate in Columbia. So I want to go through some common misconceptions about phenomena. Number one, phenomena are good to bring in after students have learned the content, right? So they learn the content and we bring in the phenomena in order to explain how the phenomena works, right? We know that's not the case, right? It starts with the unit starts with the phenomena and it drives the learning throughout the unit. There is one phenomenon per unit. Well, there's likely one anchoring phenomenon per unit, but you're going to have multiple investigatory phenomena. And the reason for that more than anything is to keep it interesting for students, right? If you have an anchoring phenomenon and that's all you're talking about for 3 or 4 weeks, most depending on the phenomenon, but likely students will get a little bored, right? So you want to bring in those investigatory phenomenons to maintain that spark of curiosity and that wonder. A phenomenon is synonymous with a hook. We learned about this in a previous session, that a phenomenon isn't a hook because it's something you're returning to all throughout the unit or lesson. A phenomenon should be fun, flashy, and hands-on. Not necessarily, right? One of the videos you could have watched as an optional resource in Module 1, Paul Anderson explained how one time teaching a middle school life science class, the phenomenon that he had students grapple with was the original data table that Gregor Mendel developed with his pea plant experiment, right? And students were just looking at the data table and trying to ask questions about it and figure it out. That was the phenomenon, right? It's not flashy or particularly hands-on, but it really sparked the questions and drove the learning necessary in order for them to achieve the standard they were tasked with learning. Another common misconception is that phenomena can be a generic science topic, like ecosystems or volcanoes. For example, you're teaching on volcanoes and you say, okay, class, we're going to start this unit by asking questions about volcanoes. On the contrary, a phenomenon should be a specific instance or event. So perhaps you could watch a video of volcanic eruption, maybe a volcano that is located close to where your students are located, and have them ask questions about that, what they're seeing in that specific video, right? So the more specific of an instance it is, the more powerful it can be. And lastly, another misconception is that the summative assessment should ask questions about the anchoring phenomenon. We got already addressed that, right? But the summative assessment should be a novel phenomenon, a phenomenon that students have not yet grappled with, which is why a summative assessment for one teacher might not be a good summative assessment. A good summative assessment for one teacher might not be a good summative assessment for another teacher if within that summative assessment there's a phenomenon that the other teacher has already talked and worked with students on throughout the unit, right? It should be a novel phenomenon to show that transfer of understanding. So X on those misconceptions. Last thing I want to do is share kind of a continuum of a teacher implementing a phenomena in their classroom. So a teacher who's brand new to NGSS likely does not use phenomena in the classroom. Once you get learning and applying some of this knowledge into your classroom, they'll use a phenomenon, but maybe as you get going, your phenomena doesn't spark a lot of curiosity in students, right? However, as you keep growing, teacher uses an investigatory phenomenon at the beginning of each lesson, but there's no continuity from lesson to lesson. So lessons are driven by phenomenon, but there's no overarching anchoring phenomenon that's tying them all together. As a teacher grows in adopting NGSS, a teacher uses an anchoring phenomenon to guide a deep inquiry process and plans out investigatory phenomena to assist in this deep inquiry process. There are a lot of amazing and, no pun intended, phenomenal teachers who are at this level. And so I want to say that before I share the last one, which is really, really advanced, I would say. And that says a teacher uses an anchoring phenomenon to guide a deep inquiry process and then develops investigatory phenomena throughout the unit that respond directly to student misconceptions. So you present the phenomenon, see what questions students have, look at their models, see what misunderstandings they have related to the phenomenon, and then plan out investigatory phenomena that specifically address those misconceptions for your students, right? So no matter where you are in this phenomenon, no matter where you are in this spectrum, obviously our goal is to move closer to this end of the spectrum. And what we're looking for there is progress, of course. That's all I have for you today. Go ahead and continue your learning.